Good evening, Dr. Jemima.
Good evening, sir.
We have 3 minutes to go.
Sir, we'll wait for another 5 minutes and let the people join. If the count increases to 100, we'll start.
Yes, please.
Okay, sir. Thank you. Sir, we'll start the session.
Yes, Dr. Jemima, we can proceed.
Thank you. Good evening, everyone. It's my pleasure and honor to welcome you all to the ATAL Faculty Development Program on Quantum Computing, organized by Division of Artificial Intelligence and Machine Learning, Karunya Institute of Technology and Sciences, Coimbatore. We are privileged to host this FDP under ACT Training and Learning ATAL Academy, which has been instrumental in fostering knowledge in emerging technologies. I extend my heartfelt gratitude to our respected Dr. Paul Dinagaran, Chancellor, and Vice Chancellor Dr. G. Prince Arul Raj, and Pro Vice Chancellor Dr. R. Elijah Blessing, and Registrar Dr. S. J. Vijay for their unwavering support and encouragement in organizing this program. A special thanks to ACT ATAL Academy for their continued efforts in promoting advanced learning initiatives across the country. Today, as we embark on this journey into the fascinating world of quantum computing, we look forward to engaging discussions, insightful lectures, and hands on learning experiences that will equip us with the knowledge and skills required to navigate in this cutting edge field. So, quantum computing has the potential to revolutionize areas such as cryptography, optimization, artificial intelligence, and complex program solving. So, this FDP aims to provide you a strong fundamental understanding of quantum principles, algorithms, and applications, ensuring that faculty members are well prepared to integrate this knowledge into this academic and their research. We are honored to have our distinguished speakers, eminent researchers, and industry experts who will be sharing their expertise and insights throughout this FDP. I also take this opportunity to appreciate the enthusiasm and participation of all the faculty members and the research scholars joining with us from various institutions. Your presence reaffirms the importance of collaborative learning and knowledge sharing in shaping the future of emerging technologies. Thank you for your active participation throughout this 5 days of FDP program. Now I have the privilege to call upon Dr. J. Dinesh Peter, head of our Department of Division of Artificial Intelligence and Machine Learning, to deliver the inaugural speech. Sir,
Yes.
thank you.
Thank you, Jemima, for the wonderful welcome address.
Thank you.
Very good evening, participants. I hope you all had a cup of coffee or tea during the evening time. And we fully understand that, you are all bit, completed your heavy workload and tired as well. But still, whatever we are going to give for your ears, I think something is going to be awesome for everybody. As a faculty, everybody should be in the mode of learning for 24 cross 7. That is the motive in which I'm working, and I strongly believe that all the faculty members and the participants who are participating in this program are also in the same mode, because we are all teachers, one of the noblest professions in the world. Yeah, I would like to kickstart this program with the inaugural address. By the way, I'm Professor Dinesh Peter. I'm head of Artificial Intelligence and Machine Learning Division, which is a newborn division in this organization, Karunya Institute of Technology and Sciences. And we are offering two programs, BTech Computer Science and Engineering AI and BTech Computer Science and Engineering AI ML. Yeah. So it's my real pleasure and honor to be here today to kick off this ATAL FDP on quantum computing. We are all gathered here to dive into one of the most exciting and game-changing areas of technology, which is quantum computing. This FTP, I think, is a fantastic opportunity for learning, sharing your ideas, and collaborating with the fellow researchers and academicians. And of course, a few industry professionals have also joined with us today. when we talk about the computing technology, for a long way, we have been using the classical computing technology, which is actually serving us till now. But now we are living in the world which is going in a very fast pace, and we have to push the boundaries of innovation, which is actually hitting the limits of us. That is where this quantum computing comes in. So it offers a whole new way of solving problems at speeds in which we could only dream of. So all the processing and the applications that we are running, we cannot wait for receiving the answers. We need to get the answers immediately as and when we feed the data into it. So naturally, for the applications like cryptography, drug discovery, and whatnot, all the AI applications, this field that is quantum computing is set to revolutionize the way we think about computation. Yeah. So let's take a moment to appreciate the vision of AICTE and the ATAL's initiative for bringing innovation and advanced learning in cutting edge technologies. So thanks to these efforts, to this team, and our academic institutions and research communities can stay ahead in the ever evolving globe tech landscape. So over the next few days, we will have the chance to explore the foundations of quantum mechanics, quantum algorithms, and real-world applications in quantum computing. So we have amazing lineup of experts, Dr. S.P. Rajamohana from Pondicherry University, who will be the resource person for today, and Dr. Saravana Kumar, who is the software architect from Bosch, who will be delivering lecture tomorrow, and Dr. Karthik Ganesh Durai. She is the founder and CEO of Quantum G Research Labs in Bangalore, and Dr. Sandeep Kumar Singh from IIT Roorkee, Dr. Monica Agarwal from IIT Delhi, Dr. Aravind Vishnu from Amrita University, and Dr. Anupam Biswas from NIT Silchar, and Dr. Hari Prabhat Gupta from IIT Varanasi, and Dr. Ahmad Elangar from Ben Suef University, Egypt. So when I look at the profiles of the resource persons, I'm really astonishing. I should really thank Dr. Jemima and the team who has meticulously worked very hard to find such a prestigious resource persons for this FDP. So I'm very thankful to the organizing team. They took a lot of efforts. So I humbly request all the participants to make use of this opportunity and get to know what exactly the quantum computing is all about, and in turn we will provide and we will transfer this technology inputs to our student community. I encourage all of you to be active participants and ask questions. Of course, we have purposefully made this Zoom meeting as a webinar mode. Of course, you are welcome to ask questions in the chat. All those questions will be listed by Dr. Jemima, and that will be asked to the resource persons one by one, so that the resource person will be able to clarify all your doubts. So no worries that you will be given a chance to talk through this Zoom meeting, because we are going to have more than 500 participants today. So if we make it as a normal mode, which is going to be highly chaotic in nature, that's why we made it as a webinar. Sorry for that. And I hope you will be having spark discussions and make the most of this opportunity to expand your knowledge and skills. A huge thanks to AICTE, the organizing team, Dr. Jemima and Dr. Ebenezer Jangam, and our esteemed speakers for today, for making this event happen. Let's make the most of this exciting journey into the world of quantum computing together. With that, I officially declare the ATAL FTP on quantum computing open. Wishing you all an insightful and engaging experience. Thank you.
Thank you, sir, for your insightful and inspiring inaugural address. Your words have set the perfect tone for this faculty development program, highlighting the significance of quantum computing and its transformative potential in the academic as well as in the research landscape. Now I have some instructions for the participants. Let me go through the instructions. Please listen to these instructions carefully. Participants, please stay back in the same link after this inaugural session. The resource person will join soon. And I have some other instructions related to your attendance as well as at the end of this sixth day, you have a final test. So you have to maintain at least 80% attendance and secure a minimum of score 70% in the final test to qualify and to get your certificate. So the feedback form is mandatory for maintaining your attendance. So the link will be shared at the end of the session. And the feedback link will close at every day 10:30 p.m. Please ensure your timely submission. I'll repeat, the participants must maintain at least 80% attendance and secure minimum score of 70% in the final test to qualify. And attendance, the feedback form is mandatory for attendance. The link will be shared at the end of the session. The link will be closed at 10:30 p.m. daily. Please ensure your timely submission. And in the feedback form, you have to enter the participant ID. That will be in the first column. So the how to know about your participant ID? I have sent an invitation mail and about this particular FDP program. So in that mail, I have attached the participant ID list as well as I have posted by today evening. I have posted again in the WhatsApp group as well. And your participant IDs will be ranges from number 1 to 507. So choose correctly your participant ID. Based on the participant ID, your attendance will be maintained by us. So this will be useful and helpful for us to maintain all 500 participants attendance on every day. So participants, if you have any doubts, you may post it in the chat box and I'll collect those questions and I'll post it before the resource person at the end of every session. So if you have any questions, please continuously post it in the chat box. I'll collect those questions. End of the session, the resource person will address all your questions. Kindly adhere to the guidelines to ensure a smooth and successful completion of the program. Kindly wait and stay back in the same link. Now the inaugural is over. The resource person will join soon. Please stay back in the same link. Thank you.
Also, one important information to all the participants. Participants need not put good evening or good morning, anything in the chat. Uh, you're always welcome to have any technical questions to be marked in the chat. But good evening and all, I think it's not required. Because when we post any important information, when you put a lot of followed by a lot of good evenings and all, the important information will go above, and the participants will be missing those information. So I would humbly request, please avoid putting good evening and all. Of course, Dr. Jemima will be posting the guidelines, everything in the chat box. Once the guidelines have been put in the chat box, please don't have any unnecessary comments in the chat. Of course, we will just make use of this facility for providing only technical inputs so that it will be shared to the participants and the answers will be received through voice. Thank you for understanding.
So based on the request, the guidelines, once again, I'll post it in the chat and you may refer for your recording your attendance.
Dr. Jemima, I think as soon as the resource person join, we'll be starting the program, right?
Yes, sir. Another 5 minutes,
Yeah.
she will join.
Yeah. Because we have informed the resource person to join at 6:30.
Yes, yes, yes. That's why we have completed all the instructions and the inaugural session.
Yeah.
She'll take another 5 minutes and she'll join. Please wait.
Yes, yes, please. Okay.
Okay.
Very good morning, Dr. Rajamohana ma'am.
நிமிஷம் அன்மியூட் கொடுத்துட்டேன். Yes, ma'am. Yes, ma'am.
The Rajamohana ma'am has joined now. We'll start the session.
Yes, please. Very good evening, ma'am.
Good evening, sir. Good evening, sir.
I want to introduce about the resource person of the day. She's Dr. S.P. Rajamohana, Assistant Professor from Pondicherry University. She has completed her PhD in the area of spam review classification using bio-inspired algorithms. With 14 years of teaching experience, Dr. Rajamohana has previously served as an assistant professor, senior grade in the Department of Information Technology at PSG College of Technology, Coimbatore. She is having a total of 17 years of experience. She has received an elite certifications from NPTEL for the quantum computing course. Her research interests include evolutionary algorithms, deep learning, Internet of Things, artificial intelligence, and quantum computing. She has published many Scopus Index journals, articles, as well as in the field of quantum computing, and she has filed and published a patent. Dr. S.P. Rajamohana has organized national and international conferences as well as conducted numerous FDP programs. She has presented her research internationally, including Nanyang University in Singapore, where she received a Best Paper Award in the year 2017, and at Gansang University in Poland in 2018. In 2019, she presented her work at Lincoln University in Malaysia. She has also been a reviewer for various journals such as Soft Computing, Springer, Hindawi, and elsewhere. Dr. S.P. Rajamohana continues to contribute significantly to her fields of expertise through her research, publications, and active participation in the academic community. As per the schedule, she will handle two sessions today. Topic of session one is on introduction to quantum computing, and topic two is quantum mathematics. That is for session two. So I'll repeat. Session one is on quantum computing introduction. Session two is about quantum mathematics. Now I request Dr. Rajamohana ma'am to take over the session.
Thank you, ma'am. Thank you.
Thank you.
Very good evening to everyone present here. And first of all, I would like to thank the management, Karunya Institute, Principal Sir, HOD Sir, and the coordinator ma'am, Jemmy ma'am, co-coordinator sir, for providing us such a wonderful opportunity to take part in the ATAL FDP titled Quantum Computing. And I also wholeheartedly welcome all the participants for this course. So you have been waiting for a 1 week to learn a lot of quantum technologies. Okay. So thank you for the brief introduction about me, ma'am. Thank you so much, ma'am. Yes.
Thank you, ma'am.
So,
Please proceed.
yes. So in this 1 week, you are going to learn about the quantum technologies, the quantum machine learning, quantum simulators, quantum algorithms, and quantum cryptography. So if you want to learn all the quantum technology, first you must know the fundamentals of quantum computing. That's why we are going to deal with today. So let us start with the introduction to the quantum computing. And these are the outlines. Today we are going to discuss about how the quantum computing, it differs from the classical computing, and already we are having the classical computer to perform our day-to-day task. Then why do we need quantum computing, and what are the principles aligned with the quantum computing? And in classical computer we have a logical gates to process the information. Similarly, in quantum computing also, we have gates and circuits to perform the data manipulation. And we also discuss about some of the quantum algorithms. And finally, we see where we exactly apply the quantum computing. Okay. First, let me start with the basic difference between the classical computer and the quantum computer. So, everybody know the operation of classical computer. We give the input and the input is processed inside the CPU and finally we get the output. This is the working principle of classical computer. So, the machine will understand only zeros and ones, that is called as bits, binary logic. So, the classical computer, it stores the information, it represents the information in the form of bits. It will take only 0 or 1. So after we give the input to the computer, it will store and process those information, then only it can produce the final results. So how the processing data manipulation will take place in the classical computer? With the help of logical gates like AND gate, OR gate, NOT gate. So we have so many gates to perform the data manipulation. And obviously, in classical computer, it uses the classical physics, which is nothing but the Newton laws. So how we calculate the momentum of particle with the help of mass and velocity at a particular time. And you are having the laptop, desktop at your office, at your home. So it will operate at low temperature, normal temperature. And all so with the help of classical computer, we are solving n number of applications. So what are the things we'll do with the classical computer? We are watching the videos, we are attending the sessions, and we are playing games, and we create the lecture notes, we use the Word document, we create PPT, so many things we'll do. But all the applications are performing well. So the error rates are very minimum in classical computer. And next, on the other hand, we move to the quantum computer. And in quantum computer, like bits, we have the quantum bits. So in this is the fundamental block of the quantum computer. So the quantum bits can be in the state 0 and state 1 at the same time. Why? Because the class in the classical quantum mechanics, it follows the principle of quant certain principles. So the principles adopts the principle talks about electron spin up, spin position, and the photon polarization, horizontal polarization, and vertical polarization. That's why the qubits can exist in both the state at the same time, spin up position and the spin down position. We mathematically represent that as a zero state and one state. And like our logical gates, here we have the quantum gates like single qubit gate, Pauli X, Y, Z, and Hadamard gate, which creates a superposition. And we also have two qubit gates, multi qubit gates to process the information. And I I've already said in quantum computer, it uses the quantum physics. So the quantum physics also known as quantum mechanics. So it follows the principle of quantum mechanics. And you cannot keep the quantum computer at your room or office or at your home. So it requires ultra cool temperature. We have to provide a we have to provide the environment with certain parameters. Then only we can keep the quantum computer and execute all the things that we'll explain in the upcoming slide. Okay. And it always, so it requires ultra cool temperature and it follows the quantum mechanics. That's why it interacts with the environment based on the electromagnetic wave and noise. It easily get the it easily dissolve its superposition edges. That's why it provides the high error rates when compared to the classical computer. So I hope you understand what is the difference between quantum computer and the classical computer. Next, we'll see how the classical computer will solve the maze problem. Everybody know the maze problem. So if you have studied the artificial intelligence, the search technology is used to reach the goal state. You are in the initial state A and you want to reach the goal state G. So the same maze problem will be solved by the classical computer as well as the quantum computer. And what is the difference between the classical computer and quantum computer? How it solves? In what way it differs? So if you see the example in the left hand side, in the classical computer, so assume that A is your starting position or you are in the initial state and your goal state is E. So to reach your goal state, you will be having multiple options. So in the classical, it follows the linear processing. So it can only take one path at a time. So first it will take the option B to reach the goal state, and again it take another path to reach the goal state, and again it take another path to reach the goal state. So at a time it can execute one path to reach the solution, to reach the goal state. But in a quantum computer, how it solves, we know it is why uh, so much of hype is given to quantum computer. It works in a parallel manner because of its superposition. It works in a parallel manner. At a time it will explore all the paths and finally it reach the multiple path. Finally it reach the goal state. That is the advantage of quantum computer. So in simple way, how to tell, for example, if you forgot the password of your laptop, what you will do, you will give password option 1 and option 2, option 3, okay, to search one by one. You are giving the option. So the same thing is happened in the classical computer to crack the password. But in quantum, at a time, it will check all possible combinations of the password and find out the correct one. So that's why it provides the quick solution to all the complex problem. Next, we'll see the difference between the quantum mechanics and classical mechanics. So everybody know the classical mechanics. So the day-to-day life we are using we are using the classical physics mechanism only because it works in the larger object. So we can find out the moving ball location, and if the object is moving from one place to another place, we can easily calculate the momentum and position. Okay, so because it deals with the macroscopic objects that we call as a larger objects. Okay, so larger objects like a moving ball, moving object from one place to another place, or moving vehicle from one place to another place. And here it provides a deterministic solution. If you know the initial state, from the initial state you can predict the future state of that moving ball or moving object. So that could be how we can find out that with the help of the Newton's law. So the state of the system is defined exactly based on the position and velocity. That is that is possible in the Newton's. So if you have a larger object like a vehicle or a ball, so the classical physics will provide a solution. But in quantum mechanics, we are dealing with the very tiny particles like atom, that is electron, neutron, photons. So these are all microscopic level objects you cannot see through your eyes. So obviously it can be in any position. So the results will be the probabilistic nature. It will not be the deterministic one. So like your classical mechanics, you can find out exact results, but here it is very difficult to find out the particle, the moving atom exact position and exact location. That's why the quantum mechanics came into the picture. So if you want to deal with a tiny particle like electron, photon, neutron, in that situation, classical physics, the classical mechanics does not work well. So that's why the famous scientist described the uncertainty principle. So in that principle, what he suggested, so in simultaneously, you cannot find out the particle position and velocity because the atom is very, very small. So atom can be in both the nature. It can act as a particle, can act as a wave as well as particle. That's why we cannot predict the position and velocity of the tiny particle. That's why it is in a probabilistic nature. And next one is Moore's law. So according to the Moore's law, every year the number of transistors on integrated circuit chips, it doubles every year. So everybody know that in the computer we have CPU, and the CPU is made up of transistors, made up of billions of transistors. So with the help of transistors only, the electric voltage is passed. If it is a high voltage, then will allow this, it allows the signal. If it is low voltage, then it close the signal. So how it will act like a switch, turn on and turn off. If it is a high voltage, it is in one state. If it is a low voltage, it is in a zero state, like true or false. So it act like a transistor, will it act like switch. So why we go for a, why do we bother about the quantum computation? Already we have a classical computer. So with the help of classical computer, we can solve all the problem. So why there is such a hype given to the classic quantum computer? So according to the Moore's law, the transistor size is reduced. Now Intel i9 core transistor size is about 7 nanometer, 7 to 5 nanometer. If we reduce the nanometer size, transistor size below 5, it is unable to differentiate which is 1 and which is 0. That's why after 2022, classical computer will not provide that much speed solution for the complex problem. That is the drawback of classical computer. So that's why we move to the quantum computer to solve the complex problem with the with a quickly. So we already have the supercomputers also. So then also we need a quantum computer. So what are the limitations of classical computer? We'll explain. So everybody know that what is computing. Computing is nothing but a calculation. If the device is able to perform some calculation, then it is called as computing device. So examples of computing devices, your calculator is a computing device, the classical computer is a computing device, supercomputer also computing device, the quantum computer also computing device. But each device has its own limitations. That's why we move on to one from another. So what are the limitations of classical computer? When we see the limitations, we as you, for example, you can take up NP hard problem. That is a traveling salesman problem. For example, if you want to sell a product from south to north, so in between you have n number of cities. Assume that if you have 30 cities in between. So in that case, what is the search size? 2 power 30 possible combinations are there to deliver a product from south to north. So now you have to think about how much memory is required to calculate and how much time is needed to solve this problem, this NP hard problem. So that is the limitation of classical computer. The computing power and complexity is very high when we solve the NP hard problem and the difficult complex problem. That's why we move on to the quantum computers. So the quantum computer will solve all the problems usually the classical computer will not solve in a proper way and proper time. Next. So what is quantum computing? So quantum computer is a machine which will perform the complex calculation. How it will solve all the how it will perform the complex calculation in an easy way with the help of quantum mechanics. So what are the principles of quantum mechanics? So with the entanglement, superposition and interference. So with the help of these quantum mechanic principles, The quantum computer is easily process, store, and manipulate the large amount of data. So it can perform the complex calculation easier in easy way when compared to the traditional computing system. And this is the IBM 53 qubit superconductor based quantum computer image. Okay, so we know that the quantum computer, it uses the quantum mechanics principle. Quantum mechanics is also known as quantum physics. So it describes the behavior of particles as well as subatomic particles. So it is a very tiny, it describes a tiny particle behaviors like electron, photon, neutron. So this idea of quantum computer begin with Richard Feynman. He is the father of the quantum computer. So we are all thinking that 2022 is the 2025 is the quantum leap year, quantum computing year. But the quantum computing exists in the year 1982 itself. Now it evolves a lot. So the term quantum mechanics is coined by the Max Born in the year 1924. This is if you want to really know the history, you can explore. After that, Shores produced the algorithm, and Groover's algorithms are there. So many algorithms came into the picture with the help of the quantum mechanics. Okay. So the in quantum mechanics, it describes the behavior of particles at the atomic level and subatomic level. So here we are consider only the electrons, photons and neutrons. And the electron, it has a property like called spin up and spin down. If it is a photon, the polarization is a horizontal polarization or vertical polarization. So the electron spin up is in a clockwise or anti-clockwise. So in quantum physics, electrons can exist in a superposition. So it can be in both the position at the same time, that is spin up and spin down position at the same time. With the help of superposition only, the quantum computer can easily solve the complex applications, and it provides the solutions in in an effective way. And this is the Google Sycamore processor. So it is a 53 qubit processor. And in 2019, Google achieved this. So within the 200 seconds, it has solved the complex algorithms, complex problems. So if you want to solve the same problem with the help of classical computer, it will take 10,000 years. So that is the great achievement of Google. Okay. Now let me discuss about the quantum properties. These are the fundamental principles of quantum mechanics. So these are wave particle, duality, superposition, entanglement, interference, quantum decoherence, and tunneling. Okay. First, we'll discuss about wave particle duality. So this is the Young double slit experiment. The famous scientist Thomas Young, he prepared in his experiment. What he does is he shoots the light photon through the two slits, and he checked the screen. So the electrons or the photons passes through the two slits, and it creates the pattern at the screen. So if you see the patterns, it shows the light pattern and the dark pattern. It reflects the interference. Okay. So electron passes to the two slit, and it behaves like a particle as well as wave. It reveals that the particle has both a nature, wave-like properties and the particle-like proper characteristics. So this is one of the fundamental principles of quantum mechanics. And next one is superposition. So superposition means multiple, the electron can be in the spin up position and spin down position at the same time. Similarly, when you toss a coin on the air, until you get the coin in your hand, you cannot know whether the coin is in head or coin is in tail. Once you get the coin on your hand, then only you know the position, position of the coin. Okay, so in classically, we don't know the state, but according to the quantum mechanics, it is in both the states. It is in head state and tail state. So that is possible because of the superposition concept in quantum mechanics. So before the measurement, it could be in both the state, head and tail state. After the measurement, once you measure the measurements, it collapses its states. You could get only head or tail. So the quantum mechanical state is well defined. There is 50% of chance being in a head state, 50% of chance being in a tail state. But in classical, it is a deterministic one. Either you will get head or tail. But in quantum mechanics, with the help of the superposition, the coin can be exist in both the state, head state and tail state at the same time. And this is the Schrödinger cat thought experiment. And he put the cat inside the box and he kept the toxic gas. If the atomic gas decays, then the cat is in dead state. If not, the cat is in alive state. So how do you know that? Until you open the box, you cannot know whether the cat is alive or not. So that's why it is called as a thought experiment. So until you open the box, you cannot know whether the cat is alive or not. So the cat can be alive and dead at the same time. Once you open the box, then you might know the cat is dead state or cat is in alive state. But before before the measurement, the cat could be in both the state. That's why it is called a superposition. Okay. And when you flip the 2 coin, the possible outcomes are this. And when you flip the 3 coin, these are the possible outcomes. But in classical computer, either you will get HH at a time, HT or at a HT, any out of all the possible outcomes, you will get any one. But because of superposition, at a time, you will get all the possible combination. That is the beauty of the quantum superposition. The next principle is quantum interference. So when it occurs when the probability amplitudes interact in a way. So when it interacts, either it reinforce each other, or it will cancel each other. So that's why it is called as interference. And it is categorized into 2 types, constructive interference and the destructive interference. So uh, the main purpose of this principle is, I've already told that if you want to reach the goal state, with the help of quantum computer, at a time it will search the multiple paths, multiple options, then it find out the correct answer. So what about the remaining answers? So the remaining options, it will cancel. With the help of interference only, it will remove all the incorrect ones and it provides the correct ones as a solution. That makes the computation more effective with the help of quantum mechanics principle in quantum computer. So the quantum interference is a result of superposition, because when you use the classical computer, either you will get a 0 or 1. It is a deterministic one. But with the help of superposition, we'll get both the state at the same time, with speed up the calculation, with speed up the computation. So we'll get the correct answer. So this is the category 1 is a constructive interference. So if you look at the image, There are two waves. The two waves are traveling with same frequency and same direction. So wave 1, we have two waves, wave 1 and wave 2. When you add these two waves, and we will get the result as the third one. So the resultant wave amplitude is much higher than the original wave because it adds the waves together. It adds the amplitude and it increases the amplitude. That's why it provides the resultant wave is bigger than the other two. So it is called as a constructive interference. And next one is destructive interference. So here also, if you look at the example, this is wave 1 and this is wave 2. When we add, both the waves are traveling in the same direction and with the same frequency. There is no change. So if we add these waves, then what you will get? You will get the flattened line. Why? Here it will cancel each other. If you clearly look at this image, the first wave is in upstate and the second wave is in a downstate. When we add these two, it cancel each other. That's why we get the flattened line. So it is called as a destructive interference. This is how the quantum computer will delete all the incorrect options, all the incorrect solution. It will remove all the incorrect solutions and produce the accurate solution as a desired outcome with the in a short time. And next important principle, important advantage is quantum parallelism. In serial computing, what you will do, will check with single keys. We'll try with all the keys one by one. It is in a linear order. And in parallel computing, what we can do, we create more number of keys and we check parallelly. But in quantum computing, we will check all the possibilities at a time. So that's called as quantum parallelism. It allows the quantum computers to evaluate the function for many possible values simultaneously. That's why it achieves the parallelism. It provides effective solution for the quantum algorithms. And next important principle is entanglement. So quantum entanglement is another important unique property. If you see the image, when the two particles are correlated with each other, then it considered as a single system. If one particle uh, position is changed, if one state of the one particle is changed or one qubit is changed, it will automatically affect the another particle because it think like that a single system. So if the state of one is changed, it affects the other qubits or other particle also. For example, left hand side, the electron is spin up position and the right hand side particle is, if it is the first electron is spin up position and obviously this one is a spin down position. If one particle is a positive, then another particle will automatically change to negative one. So it is a unique property of quantum system. When the one or more qubits are correlated with each other, the state of one qubit will affect the another qubit regardless of the distance. Means in my place I'm having one qubit and your place you are having another qubit. If my place the qubit is in positive state and your place the qubit will automatically change to the negative phase. Okay, so Einstein called this as a spooky actions at a distance. Once you measure, it could be collapses into entanglement and it will provide only one solution. And where we can use the entanglement concept. So in the quantum communication and quantum cryptography, quantum teleportation, we use the entanglement concept. Mainly the quantum cryptography and quantum communication, we use the entanglement concepts. So how far it is, if both the qubits are entangled, one qubit is changed, the other qubit position are also changed. That's why it is called as entanglement. And the next one is quantum decoherence. So, as I told in the first slide, we cannot keep the quantum computer in a normal temperature. It requires an ultra cool temperature because in quantum computer it uses it principle of quantum mechanics. So in quantum mechanics, we'll study about the particle like photons, electrons. So these are all very tiny particle. So when it interacts with the environment, so it dissolves its superposition. It lost its superposition. So because of its spontaneous interaction between the environment, it loses its superposition. When the particle loses its superposition, what will happen? It will be act like a classical one. So that's why it is called as decoherence. When the quantum computer interacts with the environment, it loses its superposition. So this leads to high error. This leads to high errors in a quantum information. That's why they are looking for the better quantum error correction technologies. This is the recent research area. And the last one is quantum tunneling. So quantum tunneling is with the help of classical computer. For example, you are at the bottom of the mountain. If you don't have enough energy to climb up, you cannot move from down to up. But with the help of quantum tunneling principle, you can penetrate through this barrier and this could be reached at the other side. So that is the advantage of quantum tunneling. So quantum where particle pass through the barriers, they should not, but that is not possible in the classical one. If you don't have the enough kinetic energy, you cannot pass through this barrier. And another one is, this is also example of quantum tunneling. When you hit the ball on the wall, immediately the ball will bounce back to you. It will not go beyond the barrier because the quantum tunneling is not possible in the classical computing. But with the help of quantum mechanics, it will easily surpass the barrier and it will go to the other side. That is possible. And this is the measurement. So the qubit state is represented with the help of wave function. So wave function is determined by the Heisenberg uncertainty principle. So the particle can have both the nature, wave as well as particle characteristics. Before the measurement, it will be in both the state, 0 state and 1 state. After the measurement, it could be collapsed. You get either one of the state as an output. So that's why the wave function, this is the symbol of wave function psi, and it is represented using alpha 0, the linear combination of ket 0 and ket 1. This we will discuss in the session 2, ket 0 and ket 1. After the measurement, either you will get ket 0 or ket 1. And always, according to the quantum mechanics, amplitude which is equal to probability. So the probability, when you take the square root only, you will get only the non-negative number. So that's why the probabilities of alpha square and the probabilities of alpha 1 square. When you add these two probabilities, you will get the 1 as an outcome. And again, this is the example of qubit measurement. In classical state, we have 0 and 1. At a time, you will get either 1 bit or 0 bit. But in the quantum world, we have n number of qubits. So these all the qubits have the superposition state. Superposition state. When you measure, it gets collapsed. It will either you will get 0 or 1. That is shown in the diagram. So possible states of one qubit before the measurement. It could be in both the states, 0 state and 1 state. After the measurement, it should be in either 1 state. And next we'll see the building blocks of quantum computing. So qubit is the fundamental unit of quantum computing, and and to process the information for the data manipulation, we need to have the quantum gates and quantum circuits. And next, so this is how we represent the qubit. So classical, we have only two different shapes, 0 and 1. After the measurement also, it doesn't affect. You will get either any one of the state. But in the qubit representation, in the quantum, qubit is a two-level system. So we can label this as a state 0 and state 1. When we measure the qubit, the probability of 0 is a probability of being in 0 state and probability of being in 1 state is 50%. So it creates a superposition. And next one is quantum gates. So like how we have different gates like AND, OR, NOT, NAND, and NOR. We also have different quantum gates to perform some operations. So quantum gates are much more complicated than the classical because the quantum gates are reversible. The difference between the classical gates and quantum gates, in classical gates which operate only on 1 or 2 bits at a time, but here the quantum gates will operate on multiple qubits simultaneously. That's why it can be easily solve the complex calculations. And these are the truth tables of NAND gate, AND gate, OR gate, and NOT gate. So when both the inputs are true, then only the AND gate will produce the one as output. If any one of the output is 1, then only the OR gate will produce the output. And in NOT gate, it's just the negation of the input. Okay. So with the help of NAND and NOR gates, we can create more number of gates. That's why it is called as universal gates. And the classical gates are irreversible. So what is reversible and irreversible? With the help of output, we are not able to get the input. For example, in the AND gate, the output is 0. Okay, for this output, we have three different combinations, 0, 0, 0, 1, and 1, 0. So based on the output, I cannot get my input. Okay, so that's why it is called as irreversible gates. But with the help of quantum gates, we can get the inputs based on the output. That's why the quantum gates are called as reversible gates. Similarly, based on this output 1, you cannot get the input values because in OR gate, the 1 is output for 3 different possible combinations. So based on the output, you cannot predict the inputs. That's why the classical gates are called as irreversible gates. And these are the different types of gates which is used in the quantum computing: X gate, Y gate, Pauli X gate, Y gate, Hadamard gate, which creates a superposition. And we have control NOT gate. It operates like our XOR operation, XOR gate, and swap gate. And this Toffoli gate is a multi-qubit gate. When both the inputs are 1, then only it will change its outcomes. And Hadamard gate, it creates the superpositions. And these Pauli gates, X, Y, Z gates, X gates are just a bit flip gate. If you give 0, it gives 1. It will negate the gate. If you give 1, it produces 0 as the output. Okay, it just flip the state of the qubit. And Y and Z gates are similar, but it introduced phase shift in the operations. And next we'll see the quantum circuit. So this is also similar to the classical circuit. And the quantum circuit, we have the ordered sequence of quantum gates. So here the measurements will be left to right. So after the measurement, you will get the output as a classical one. So these are the inputs, K0, K0, K0. These are the inputs. And H, X, Z, X, Z, these are the single qubit gates. After performing, and these are the 2-qubit gates, after performing the gate operation. So then it will produce some results. After the measurement, we'll get this results. And next, so with the help of quantum computer, with the help of the quantum gates and circuits will do so many calculation and process. For that, we need to have the algorithms. That's why we have quantum algorithms. The famous quantum algorithms are Shor's and Groover's algorithm. So Groover's algorithm, if you want to find out the factor for a large prime number, it is very difficult. So RSA encryption is based on that only, but easily it can cracked by the quantum computer. So we can easily find out the large factoring of large prime number. When you multiply two integer, and you can easily get the output with the help of classical. But if the number is large prime, then factoring is very difficult. That is called the Shor's algorithm. And Groover's algorithm is a Groover's search algorithm. Groover's search, assume that you have a millions of records in your phone book and all the names are in the sorted order, but the numbers are not in the order. If you want to search that particular number, a particular number name, then you have to search one by one. So for example, if you have 50,000 records in your phone book, then the possibility search, you have to spend the half of the amount, that is 25,000. Order of n times you need to search. So that could be easily solved with the help of Groover search algorithm. How it is possible? Because of the superposition. At a time, you are able to get the multiple states. So with the help of multiple states, then with the help of interference, it will provide the appropriate phone number for that person. And the last one is block sphere. So in order to visually represent the quantum states, we use the three block sphere. Okay. So it is a geometric representation of qubit state. North pole, it is used to represent the gate 0, and the south pole, it is used to represent the gate 1. So if it is in a spin up position, that is in a gate 0 state. If it is in a spin down position, it is in the gate 1 state. And these are the different types of quantum computers. So based on the application, they have invented these are different quantum computers. Quantum annular, it is same like a traditional computers, and this is for the analog computer. And this one, universal quantum computer, this will be applicable to solve all the real world applications like quantum machine learning, quantum cryptography, and the optimization problem. And the quantum application, where exactly we can use the quantum computer. So we are talking about the small particles like particle like electron and photon. So we can use that concept in the quantum chemistry in order to identify the molecule, and pharmacy for finding out the drugs, different drugs, and climate for weather prediction. From you can find out the cyclones. And quantum finance, it is used for analyzing the stock markets. And the cryptography, that RSA encryption and decryption, we can use the quantum algorithm. So quantum will be applicable in all the areas, not only the computer science, it will be applicable for all the domain. And the main advantage of quantum computing is because of its superposition and entanglement, it provides exponential speed up. When you take the classical computer as an example, the two possible states are 2 power n. So at a time you can take either 0 or 1. But in quantum computer, it is exponential. It is the power is exponential. So 2 per at a time it will take all possible in 2 power n combination. And with the help of the superposition, it achieves the quantum parallelism, and it will solve and provide the optimal solution for all the problems. With the help of quantum interference, it will remove the incorrect one and it produce the correct one. And the secure communication also, we use the quantum interference and quantum tunneling. It avoids the security data breaches. And these are some of the open source quantum software. With this simulator, you can try the quantum algorithm. QSKIT, it is developed by the IBM, and SICK is Google's one. So with the help of these simulators, you can try how the quantum gates will work, what are the probabilities of the different gates, how the quantum algorithms work. You can check all the things with the help of these simulators. It is open source only. You can check. And these are the references. And I hope everybody learned about some fundamentals of quantum computing. So quantum computing, it follows the quantum mechanics. And so we have discussed about different quantum mechanics principles like superposition, entanglement, wave particle duality, interference, and decoherence. So with the help of these principles only, the quantum computer will provide, it can easily solve the complex problem and provide the accurate solution in an effective way in a short time. So with this, I'll complete the session 1. I hope you could understand some of the fundamentals of quantum computing.
Ma'am,
Ma'am, yes, ma'am.
there are some of the participants, they have posted their questions in the chat box.
Okay.
Can you go click on the chat button in the bottom in your screen and just go to the chat bar.
Okay, they've asked about the superposition and okay. Okay, this is the example of young double slit experiment. In this experiment, what he has done is he shoot the electron beam through the two slits. The two slits are nothing but through the two holes, he passes the light. Here it shows the electron, but in the experiment, he passes the light photon. So the light photon passes through two slits and it creates a pattern on the other screen. Okay, so the light photon is a particle, but in the pattern which create it like a wave. That's why they call this a wave particle duality. So the particle can act as a wave-like and particle-like characteristics. So that is proven by the Young double slit experiment.
Ma'am, they have asked the difference between traditional sensors versus quantum sensors.
That we didn't cover, ma'am. We have
Okay.
discussed about only the classical computer and quantum computer. And the superposition, they've asked about the superposition. So this is the example of superposition. It is a thought experiment, not the real one. So how the superposition concept comes into the picture of quantum computer? Because we follow the quantum mechanics principle. So in the Schrödinger cat thought experiment, he kept the cat inside the box with a toxic gas. If the toxic gas decays, cat can be in the dead state. Otherwise, it could be in the alive state. So how do you know whether the cat is alive or dead? Until you open the box, you cannot know whether the cat is in which state. Okay, once you open the box, then only you may know the cat is in dead state or alive state. But inside the box, the cat could be in both the states. Both the state means alive state and dead state at the same time. So that's what written in this example also. So quantum mechanics says that the electron be in both upstate and downstate at the same time. That's why it is called a superposition. According to the classical mechanics, the coin will be in any one state, either in a head state or tail state. It will, at a time, it will not be in both the state.
Ma'am, shall we go for the next question?
Yes, ma'am.
How can we say high error rate in quantum rather than classical methods?
Yes, we can keep the classical computer at the room temperature. We can operate the classical computer at room temperature. But in the quantum computer, it operates at the atomic level and subatomic level. So electron, photons, neutrons. So when it interacts with the environment, it easily get lost in the superposition. So it doesn't provide the proper results. So if it loses the superposition, then it behave like the classical one.
Ma'am, shall we go for the next question?
Yes, ma'am.
How can we assign our input text or values into states of direction in quantum? Shall I repeat?
Where it is.
How can we assign our input text or values into states of direction in quantum? It's in the top
So
chat.
with the help of the state vector, so the qubits are represented with basis state, get 0 and get 1. That we'll discuss in the next session, ma'am.
Okay, ma'am. Can you repeat dual nature of matter?
Ma'am, I've repeated already.
Okay, thank you, ma'am.
Yeah, if you want to work in a quantum machine learning, you can use Pennyland. And apart from IBM Qiskit, you can go for a Pennyland also.
The classical system also works in parallel computing process. How does quantum computing differ from classical computing? And followed by the question, could you give some explanation of the rotation gate? How it will influence the quantum circuit
I
design?
Ma'am, I have not covered the rotation gates, ma'am. So the phase gates, they've asked about the phase gates. I have not covered that, ma'am. It's just an overview of what the quantum computing, ma'am.
One of the participants is having a doubt. Is it necessary to study quantum mechanics and
Yes,
quantum physics?
yes, yeah, yes. You just go through these 6 principles to understand the quantum computing in a clear way.
And tell me some quantum simulator for healthcare applications.
Yes, you can do all the healthcare related application using IBM Qiskit, or you can also use IBM, Xanadu Pennyland.
Many questions are posted.
Uh,
I couldn't. Can we relate quantum computing with VLSI?
VLSA applications also, oh, we can use quantum computing, but I'm not sure about that, ma'am, because I'm from computer science background. I do not have much idea about the VLSI, but
Okay.
it is possible.
That's all about the doubts, ma'am.
Okay, can we take a 10 minutes break and we'll start again, ma'am?
Yes, yes, yes. So
Okay.
participants kindly stay back in the same link and you can go for 10 minutes break. And after that, the session continues and the feedback form will be shared at the end of the second session. So stay back, please. You can go for 10 minutes break and please join. And
Yes,
in
you have, ma'am. Yes, ma'am. Yes, ma'am. And if you hear all the quantum mechanics principle first time, it will be weird to all. So you have to learn all the principle again and again. After thrice, if you could read the quantum mechanics principle, then only you are able to understand what it is.
Okay, ma'am. Thank you. You have cleared all the doubts of our participants so far, whatever they have asked in the chat box. So in the chat box, efficiently use it for interaction. So audience participants, you are encouraged to post your questions and any doubts if you have, please post it here. We are ready to address. Thank you, ma'am. Thank you. And now we can go for a break. Today there is only one feedback form will be shared for both session combined together, one feedback form. So no need to worry about it. At the end of second session only, you will get the feedback form. So please stay back here, and after 10 minutes, we'll start the next session. Thank you all. Thank you, ma'am.
Yes, ma'am. Can we start?
Yes, ma'am, please.
Yes. So welcome back you all for the next session on quantum mathematics. So the mathematical foundations for quantum computing we'll discuss in the session 2. So this we have already discussed. In classical computer, bit can be in two different states, 0 and 1. When you measure, you will get either 0 or 1. But in the case of quantum bit, the qubit, it is a two-level quantum system. It can be in 0 state and 1 state simultaneously. So that is a linear combination of base state, and it is specified with a wave function. So Heisenberg uncertainty wave function. Okay, so simultaneous. Okay, and next we'll see, according to the physics, the vector is a quantity which has magnitude and direction. Everybody knows that. And in mathematics, in linear algebra, vector is represented as a column matrix. And in quantum computing,
Ma'am,
vector,
PPT is not opened. PPT screen is not shared. Can you just check, ma'am? Once again, can you click on the share button and
this one.
share screen and then which
Okay,
PPT?
okay. Now it is visible.
Yes, ma'am, visible now.
Okay. Okay, quantum bits are represented as a linear combination of basis state. The basis states are ket0 and ket1. So this is the physical state of the quantum system is represented by the wave function psi. And according to the physics, the vector is a quantity which has both magnitude and direction. Magnitude is nothing but the length of the vector. In linear algebra, the vector is represented as a column matrix. And in quantum computing, we represent the vector in a two-dimensional complex vector space that is called as a Hilbert space. Here we have n dimensions. So the dimension can be the finite or infinite dimensions. And we use the Dirac notations to represent the qubit. So the Dirac notation, or it is called as bracket notation. So this is the bracket notation or Dirac notation. So the qubits are represented in the Dirac notations. So we use vectors to represent the qubit. In classical computer, we use single digit 0 and 1 to represent the two base state. But in quantum computer, we use the ket0 and ket1 vector to represent the qubit 0 and qubit 1. Okay, so the ket representation is vertical axis and the angular braces. This symbol is used to represent the ket notation. And this ket0 is a column matrix. This is the column vector. So ket is a column vector and bra is a row vector. We'll see one by one. So these are the base state representation of qubits. And so ket notation is ket is a column vector and bra is a row vector. We have to take the complex conjugate transpose of the ket that is called as a bra. So this is the example of ket. It is simply a column matrix. So if you want to change this to bra notation, then what you have to do, the column. So we have to change the column to row. It is the first one. And then you need to change the symbol, change the sign. If it is in minus, then you have to change the sign to plus. If it is plus, you have to change the imaginary part symbol. That's it. That it is called as, it is in a bracket notation. So bra is similar to ket, but the values are in row, and each element we should take the complex conjugate. Okay. And this is the example of column vector where C1, C2, C3 are a complex numbers. and this one is represented as a row vector. So what is BRAC? How do we represent the BRAC? We take a transpose, complex conjugate transpose of KIT is called as a BRAC vector. Why do we use these two vectors? In order to represent the quantum bit basis states. And with in quantum mechanics, the probability which is equal to amplitude squared, that's then only you will get positive number. The probability equals the amplitude magnitude squared. This is the fundamental rule. Okay. And if the states are alpha 0 ket 0 plus alpha 1 ket 1, this is the basis state of the classical bit. But when you assume, sorry, this is the quantum bit representation, mixture of both zeros and ones. We have to normalize the state, then only we get the positive number. So always the probability equal to amplitude square. So alpha 0 square plus alpha square. So the probability outcome will always be 1. Okay. And alpha 0 and alpha 1 are not always the real numbers. We can have the complex numbers also. So complex numbers are nothing but negative numbers. But when you measure alpha 0 and alpha 1, it will not be in the qubit state. You have to measure the alpha square and alpha 1 square. Okay. Then we'll see some of the fundamentals of the vectors. So what is vector? How do we represent the vector? What are the properties of vector? And what is the vector decomposition? How do we represent the vector in the form of generalization? We'll see one by one. So these are the examples of scalar. So we know the scalar is a single number. It has only magnitude. It doesn't have a direction. So so length and temperature, time is example of scalar. So all the real numbers are scalar. And vector means we have both magnitude and direction. So these are the examples of vector. If you see all the example, we have both magnitude as well as direction. That's why it is called as a vectors. So how do we represent the vector? How do we represent the vector? With the bold letter, we represent the vector. And the magnitude of vector is nothing but the length of the vector that is written by modulus of A. So why do we learn vector? Because in quantum computing, qubits are represented with vectors only, ket 0 and ket 1. Ket 0 is a column vector and ket 1 is a row vector. And how do we represent the vectors in a Cartesian plane? This is the Cartesian plane. We have the real xy axis and A is 3, 3. So the value with the x-axis and B is a 3, the value in the y-axis. So 3, 3, 7, 8. So this is general 2D vector notation. Vx represent the value of x in the value of vector in the x-axis. Vy represent the value of x y in the y-axis. This is 2D general. Sorry, this is the general 2D vector notation. And the difference between scalar vector and matrix tensor is scalar is a single number. We have only one single value. Vector is a 1D array of number. And in matrix, we have rows and columns. It is a 2D array. If the value more than 2, then it is called as a tensor. And these are the representation of three vectors in a Cartesian plane. Ax, Ay represents 2, 8. So the 2 is the x-axis value and 8 is the y-axis value. So this is how we represent the vector in a Cartesian plane. And how do we plot 3, 4? 3 is the x-axis value and 4 is the y-axis value. So this is the general 2D vector representation in the Cartesian plane. This is called as Cartesian plane with two coordinates x and y. And again, this is also one of the example. Okay. So why do we need Cartesian coordinates? So in order to locate the position of the particle, position of that point where we have that particle, we need to have the Cartesian coordinate or polar coordinate. As I said earlier, uh, the qubits are represented in a block sphere. So that's why we use the polar coordinates to locate the position of the qubit. Okay. We can also identify the state of the qubit with the help of Cartesian coordinates. So how do we locate the polar coordinates in the block sphere? So here R represent the radius of the circle. So this indicates the distance between starting to a particular point. And the second one, we need to have the theta value. So the theta value is a right angle phase value. So in the quantum computing, the polar coordinates, which is used to represent the state of the qubit. So radius, so this radius represents magnitude. Magnitude is nothing but length of the vector. And the angle represents the phase. So with the help of the angle and radius, we easily identify the location of that particular qubit. Okay. That's why we use the block sphere to represent the qubit states. And this is the example of Cartesian coordinates. How do we represent the states in a Cartesian plane? And this is the representation of polar coordinates. So here the x is r cos theta and y values are sin theta and angle theta is in radians. So this is the angle theta. So if you know the r value and theta value, you can easily identify this point. That's why the qubits are visually represented in the block sphere. And to find out the length of the vector, we use this formula, the value of x square and value of y square. Then you will get the length of the vector. And the direction of vector will be calculated with this formula, the tan inverse Vy by Vx. Okay, if it is in a 2D, we can use only x and y dimensions. And if it is a 3D, then we can add one more dimension, z. And this is how we calculate the vector magnitude. So how do we calculate the vector length from origin point to this point? The square root of x-axis value and the square root of y-axis value, which will provide the vector length. So the vector length is 6. Okay. So vector length is otherwise called as modulus or magnitude. And the direction of vector is calculated with the help of these formula. Alpha, beta, gamma is calculated with the help of these formula. If it is perpendicular, the value is 1. That's why it is called as unit vector. So the direction of vector is theta. It is calculated using this formula, tan inverse the y value divided by x value. So if you substitute the y and x value, then you will get the angle of this vector. And you just calculate the magnitude and direction, this vector 6, 6. So if you take the square root of x and y value, then you will get the length of the vector. And if you apply this formula, then you will get the angle of that vector. And next one is vector operation. So we can perform vector addition. You just add the two vectors 3, 6 and 5, 3, which will give 8, 3, 8, 9. This is a vector addition, normal vector addition. And vector multiplication, we can multiply vector with scalar. Here the c is a single number, it is a scalar. We just multiply 2 with the vector 4, 5. So we multiply 2 with 4 and we multiply 2 with 5. And finally we get the vector 8, 10 that is plotted in the Cartesian plane. This is vector scalar multiplication. And the next one is vector decomposition. So here the vectors is represented. If you put a cap on this, then it is called as a unit vector. This is unit vector 1, 0. and 0, 1. The probability of being in 0 state is this, and the probability of being in 1 state is this vector. Okay, so we just decompose the vectors. So vector values 3, comma 3. If we multiply vector with scalar, then you will get 3x cap plus 3y cap. This is how we perform the vector decomposition. It will increases the x-axis in one dimension and y-axis in the one dimension, because the unit vector is 1, the radius is 1. Vx into x cap plus vy into y cap. It represents the unit vectors. That's why it shows this direction 1 and it shows to y-axis 1. And these are the general vector representation. We calculate the vector magnitude with the modulus operation and will perform addition, and we can perform vector scalar multiplication. And a normal vector is represented as a column vector. Next, we'll move to the complex number. So why do we need complex number? And how do we represent the complex number in vector form and polar form? And why Euler's identity required? We'll discuss all the things one by one. Okay, everybody know the complex numbers are a vector complex number. So everybody know the complex number is nothing but a real number as well as the imaginary number. It consists of both real and imaginary component. This is the imaginary unit and this is the imaginary coefficient. That's why it is called as a complex number. So how do we represent? We can represent the complex number in a 2D complex plane. So this is how we represent the complex number in a complex plane. So this axis is a real axis, x is a real axis, and this axis is a y, imaginary axis. So A unit in the horizontal direction and B unit in the vertical direction. This is how we represent the complex number in the complex plane. So why it is called as complex number? Because it has an imaginary part, 3i. That's why it is called as, if it is a real number, we specify 2, 2. That's it. And it's similarly the same way how we calculate the magnitude for the vector. The same way here also we calculate the absolute value for the complex number. We just take the square root of x value and y value. It gives the distance between the origin to the point. This is the point. So you just take a square of 2 square and 4 square and it will give 20. Okay, this is also one more example how to find the modulus of complex number. Okay, if you take the square, you will get the modulus value. And the next one is how to represent the complex number in polar form. Because in block sphere, we use spherical coordinates to represent the qubits. Okay, the polar form of complex number expresses in terms of angle theta and the distance r. So with the help of theta r and the projection phi, we can calculate where exactly the qubit, in which state, which position. Okay, and this is the formula of polar coordinates. X equal to r cos theta and y equal to r sin theta. To find out the r value, you just take a square root of x square and y square. This is the trigonometric form to represent the complex number in polar form. If you understand this, then it is easy to visualize the block sphere. So again, the theta is used to indicate the angle of that vector direction, polar coordinates direction. These are the formulas. Okay, the polar form of complex number with coordinates is written as z equal to r cos theta plus I r sin theta. So you can rewrite like this, r cos theta plus I sin theta. And the radius is calculated with the help of magnitude formula, that is square root of x square plus y square and theta, which is equal to tan inverse of y by x. So R is nothing but the length of the vector. So the modulus of the complex number. Theta is nothing but it is argument of the complex number. That is angle of the complex number. So here the theta is pi by 2. Okay, next we'll move to the complex conjugate. So complex conjugate. So in the qubit representation, the q alpha square and beta square. So what we have discussed, what I said in the qubit representation, alpha 0 and alpha 1 are not always real numbers. So we can have the negative numbers. That's why we go for a complex number and complex conjugate also. In order to represent the imaginary parts also, we need to have the complex conjugate and complex numbers. So how do we take the complex conjugate? If we just modify the sign, a plus ib is written as a minus ib. If z is 2 plus 3i, then you just modify the sign of the positive to negative symbol. And you can plot the 2 plus 3i in the Cartesian plane and 2 minus 3i at the bottom. And we can compute the absolute value of complex numbers also. And this is the 3D vector representation. We have all the dimensions, x plane, y plane, and z plane, and the coordinates are a, b, c. In 2D, we have only x, y, but in 3D, we have x plane, y plane, and z plane, and the coordinates are a, b, c. If you want to locate the particle p, assume that you have a particle p. If you want to locate the particle p, you need to have these coordinates, a, b, c coordinates. Okay. Now we'll move to the next one. So how to visualize the qubit, we are using the block sphere. So this sphere will have ket0 and ket1. So ket0 represent the north pole and ket1 represent the south pole. And inside the sphere, we have 3 planes, x, y, z planes. So assume that apart from ket0 and ket1, we'll be having more number of qubits. So inside the sphere, we can have n number of qubits. So assume that if you want to find out the location of this particle, with the help of spherical coordinates, we can easily identify this particle location. For that, we need to know always this point is connected with the center. So center. So the radius is always 1. It is a unit vector. So r is always of 1. And with the help of theta, we can measure the angle. And if it has a projection, you will be getting the phi. So the spherical coordinate, with the help of spherical coordinates, radius, theta, and the projection phi, you are able to identify the particle, the state of the qubit. So north pole we have ket0 on x z plane, and south pole you will be having the ket1. And any state can be represented. So apart from the north pole, the ket0 and ket1 will be having more number of state inside the block sphere that could be represented with the help of this formula. That is wave function cos theta by 2 ket0 plus e power I theta sin theta by 2 ket1. So if you want to find, you assume that this is your state of the qubit. If you want to find out the location of this particle, you need to know the theta, r value and phi value. Then you can easily identify this particle location. And with the help of trigonometry, you just substitute the values in this formula based on the angle. You just substitute the value, you will get the different qubit positions. Assume that if the theta is 0, the angle theta is in a 0th position. So it is perpendicular to each other. So there is no shadow. So if we apply theta to 0, you will get ket0 position. if you change the angle, if the theta is phi, then it will move to the down state, the spin down state. That's why the theta is moved this to this. The radius is 180. Okay. If you are standing at this straight, you will not have any projection. That's why the phi equal to 0. If you substitute these values inside this formula, you will get 1. And similarly, you will get the superposition and explain and then explain and superpositions of with imaginary, and these are the multiple qubits in the block sphere. But in classical computer, you have only 0 or 1. So one classical bit has 2 power 1 possible states, 0 or 1. But in quantum computer, one of these qubits has order of 2 power n accessible states. Okay. And why do we need Euler identity to represent the cos theta and sin theta, the polar coordinates? Because when you want to make a complex number multiplication or a complex number division, then in that situation you can use the Euler identity. It is nothing but e power I. It's a exponential form. How it grows? Exponential means it keep on growing. It is a simple way of representing the polar coordinates in the block sphere. That's why we use the Euler's identity. And these are the operations. When you substitute the phi in the formula, you will get the values. Next, we'll move to the inner product and outer product and tensor product. Okay. So if you want to make a product of two quantum states, ket psi and ket phi, then it is called as a tensor product. It produces a column vector. We'll see this. So this is a column vector and this is also column vector. So ket psi and ket phi is called as a tensor product. It produces column vector. When you multiply two column vector, the result also will be the column vector. If we square all the individual vector, the sum value will be 1. Okay. So, why do we need the tensor product? Two qubits are represented. Single qubit is represented is with ket0 and ket1, column vector and row vector, and two qubits are represented with the tensor product. When you multiply two column vector, you will get the resultant as a column matrix only. So in classical bits, two classical bits, the possible states are 0, 0, 0, 1, 1, 0, 1, 1. So listen carefully. So if in classical bits, two-state classical bits, these are the 4 possible outcomes. So you will get any one of the outcomes as a result. But in a quantum computer, these two qubits at a time, you will get all possible combinations of the two qubits taken together. That's why it is called as superposition. At a time, it will check all possibility and then it will produce the correct one and it remove the incorrect one with the help of interference. Okay, that's what discussed in the interference and decoherence. And wave, the qubits are represented with the help of wave function. So all the probability of qubits existing in one state, 1 0 state, 0 1 0 at a time, you will be having all the state. All the states are exist at a time, that is represent with the wave function. And these are the basis state of two qubits, 0 0 0 1 1 0 1 1. If you multiply ket 0 ket 1, you will get these values. If you multiply ket 0 ket 1, then you will get these values. These are the simple multiplication. And similarly, to represent the 3 qubit, we need to have a basis states. They are ket 0 0 0 0 1 0 1 0, etc. And the calculation for the 3 qubits are shown here. Ket 0, ket 1. First, we need to perform a tensor, and then again we need to perform tensor. Then finally, you will get the this single column matrix. So far we have discussed about the tensor product for 2 qubit and 3 qubit. Now we'll move on to the inner product. So inner product is similar dot product, how we use dot product in machine learning. The same way here also we use the inner product. We just multiply the row vector and the column vector. So it produces the numbers as a result. So this is the example of the inner product of block A. So block A means we just convert the column vector into row vector. So row vector and this is the column vector. What is the results? We get only the numbers AI, BI. So this is the example of. So here they have given bra vector as a 3i2 and the ket vector as a column vector. If you we multiply these two, the final answer will be the number. And this is again one more example. If you multiply the column vector with complex number, the resultant value will be complex number. That's it. And this next one is outer product. So the outer product, we just multiply the column vector with row vector. The resultant number will be the matrix one. It will not provide any number. The result will be in the matrix form. So the product of two quantum states, if you multiply these two, then the result will be in the form of matrix. It produces the matrix. So outer product generally gives a matrix, and inner product, it provides a number which can be complex valued. So if one of the vector value is complex, then the resultant value also the complex value. That's what written here. So we have discussed about vectors. How do we represent vectors in physics and in linear algebra? How the vectors are represented? Why do we learn about the vector and polar coordinates? Because with the help of uh, polar coordinates only, we understand the Bloch sphere. With the help of vectors and vector representation only, we learned about how do we represent the qubits in the quantum system. The state of the vectors and base states are represented with the help of vectors only. So that's all about the second session. Thank you all for your patience listening for both the session. I hope you all understand the basic fundamentals of quantum computing, quantum principle, and quantum mathematics. That is vector concept and polar coordinates. How do we represent the vectors in a Cartesian form as well as polar form? In order to visualize the qubit in a Bloch sphere, we need to know the polar coordinates, that is spherical coordinates. So if you listen listen the lecture once, you can able to understand 50%. Again and again you sit and learn, then you will be familiar about all the quantum principles and quantum computing fundamentals. Yes, ma'am, yes, completed.
Thank you, ma'am, for your enlightening sessions on introduction to quantum computing and quantum mathematics. Your expertise and clear explanations have provided a strong foundation in this field. We truly appreciate your time and effort in sharing your knowledge with us. I hope the participants also witnessing the same, and you can also experience the same by reading their messages in the chat screen. Thank you. Thank you, participants. With this, we'll wind up the session. Now I request ma'am, if you want to leave, we can leave, and the audience, sorry, participants can go for marking their attendance. I'll post the attendance now. Okay.
Yes, ma'am. Thank you for the opportunity, ma'am. Thank you so much.
Thank you, ma'am. Thank you. Thank you.
Thank you all the participants for your patience listening. If you have any doubts, you can contact me. You can get my number from Jemima, ma'am.
Thank you, ma'am. Thank you. So this is for your attendance. Please mark your attendance. I've posted the link in the chat screen. Kindly enter your feedback in this attendance link. Please enter your feedback form. After that, you can leave. Thank you. Thank you, participants. Tomorrow's session starts at 6 p.m. Please join. After marking your feedback form, you can leave from this link. Thank you, participants. Once again, I'm posting the link for your reference. Please mark your attendance. There is only one feedback form today. Please enter your attendance. For participant ID, please refer the PDF that we have posted in the WhatsApp group as well as we have communicated through email. Thank you, and you can leave. Good night, all of you. Thank you, you can leave. Yes, we'll try to get the PPT and share with you. After marking attendance, you are requested to leave from this link. Thank you all. ID, please refer WhatsApp as well as your mail. There is a PDF I have shared with you. Kindly check your ID from there. It's from number 1 to 507. Check the WhatsApp or the first mail that you have received from me. Click the link or you copy paste the link in your browser. You can able to mark your attendance. You have got this meeting link in your mail, right? The same mail when you go, you can able to see in the attachment the participant ID and the registration list is attached. Kindly check that one. Please join the WhatsApp group. The WhatsApp group link I have communicated to you through the first mail. So the mail that you have received from me, so please go back and check. Your attendance you have to record in this link. Click this form and you have to fill the feedback. That is going to be counted as your attendance. Yes, after marking your attendance, you can leave. Thank you. If you want, I'll post the same link again. Thank you. Please mark your attendance. After that, you can leave. If you have any doubts, post your doubts here. Thank you. Don't forget to record your attendance in this feedback form. Thank you all. Thank you. Okay, good. Thank you. Once you have entered your attendance in this feedback form, when you click this form again, your response will not be accepted. That means your attendance is already marked and recorded by you. Okay, thank you for your suggestions. If you fill the feedback form, that is counted for your attendance. There is no separate attendance link. Only one feedback form. While you enter the feedback, that is counted as your attendance. Yes. Attendance and feedback form in one form only. Thank you. After marking attendance, you may ask to leave from this link. WhatsApp group link, you please check the first mail that you have received from me. We have split the number 1 to 250 in WhatsApp group 1 and the remaining numbers in the second group. So please click on that link and then join. If you want the attendance link once again, okay, click that. Thank you. Once again, I have posted the attendance link. Mark your attendance. Okay. I posted the attendance link once again. There's a feedback form and attendance link available in one single click itself. You fill this one single form, that is fine. If you have any doubts, post your doubts in the chat screen. After marking your attendance, you may leave. Once again, we are posting the feedback link. Mark your feedback. In the first mail that you have received from me, please read my message. When you go down, you can able to find out the WhatsApp link. Durga Meena is registered in 2 IDs. Ma'am will respond you back. Once again, I'll check your ID. You're saying your ID is registered under 2 numbers. So we'll check it and we'll respond you by today or tomorrow. Thank you. Once you have marked your feedback, you can leave. This cannot be posted there. So whoever is joined in this meeting link here itself, you have to give your attendance, and that cannot be posted over there because some participants may not join for this session. Straight away, they'll mark their attendance over there. So we are instructed that we have to post the attendance link here in this session itself. So kindly mark your feedback here itself. If you want, once again, I'm posting the attendance link. Please mark it. We have sent email to all the registered participants. So only those registered participants are connected here. So please check the mail from me, where maybe you can check your spam folder as well. You have to join through the WhatsApp group link by clicking that link, and you have to join. So kindly do it. So once again, you go back to your email, the first email that you have received the information about this Zoom link. Okay, in the same mail itself, I have given the WhatsApp group. When you just go down, little down, you can able to read the text about the WhatsApp group link. Sorry, we cannot send the mail again to any individuals. So once it is sent, please go and search it. Okay, thank you. After filling the feedback form, you are requested to leave from this link. Thank you. We are about to close this meeting. Thank you. Participants, you can leave from this link, and we'll meet you tomorrow. Can you please share the form once again? Okay. I'm posting the link once again. Please mark your feedback. Don't post your ID here. Straight away, you mark your feedback in this link itself. After marking your feedback, kindly move from this link. Thank you for the feedback. Kindly fill your feedback form and then move from this link. Thank you all. Thank you. I'm closing this meet. Thank you. There are no any action performed. Click on the link. You just copy paste in your browser. You can able to see the form. So while you click on this link, the form will be open definitely. Please check from your mobile phone. Copy paste in the browser URL, or otherwise you just double click on this one. You can able to see here. It's open, but I don't know my ID. Sir, you have to find your ID by going to my first email that you have received from me. I have shared one PDF in that mail. So you have to find your name and the ID. ID number will be from 12507. So find your ID and record your ID for further attendance updation part. So otherwise you can check the WhatsApp group. There also I have posted today. Go to my first email that you have received. There I have given this participant list ID as an attachment. Know your ID by this way. Go to the email that you have received from me in the attachment. Oh, good. It's available. Thank you. After marking your attendance. Okay, good. Please leave from this link. Thank you. Kindly leave from this link once you have successfully submitted your feedback. I'm posting it once again. After marking your attendance, kindly leave from this link. So in the same mail, if you go down and check the attachment, this ID details will be attached. So please open the mail and go to attachment, and you can able to find out the participant ID. After marking your attendance, kindly leave from this link. If anybody is having any issues, please post it here. Yes, after giving attendance, you can leave. You have to mark your ID and other details in the feedback form only. Ma'am.